introduce today's speaker, Professor N.V.Umamahesh, to you. It is very honor and privilege for me to introduce Dr. N.V.Umamahesh to you. I am very fortunate. I am a student of Professor N.V.Umamahesh at NIT Warangal. Sir has completed his graduation in civil engineering from Osmania University and MTech from IIT Kharagpur, and then PhD from NIT Warangal. Sir has started his career as lecturer in civil engineering in REC Warangal from 1987, and then becoming assistant professor in civil engineering in 95, and then promoted to professor in same department and in NIT Warangal in 2004. Since then, sir has been working as a professor in NIT Warangal. He was visiting faculty at AIT Bangkok in 2007 from August to December. Sir area of interest are reservoir operation and management, hydrological analysis and modeling, irrigation management, watershed management, water resource systems, water quality modeling and management, remote sensing and GIS applications, and neurofuzzy applications in water resources. Sir has guided more than, I think, 10 PhD scholars, and presently 8 students are working under Professor N.V.Umamahesh, and he has guided more than 90 MTech theses and published more than 35 international journals and 5 national journals and 15 national and international conferences. Sir has handled 7 major projects worth more than lakhs of rupees. Okay, has received many awards. A merit certificate for the paper presented at Second International R&D Science of CBIP held at New Delhi during 1996, and a state level Jalamitra Award conferred by Government of Andhra Pradesh, and GM Navate Award for the best paper presented at National Conference on Hydraulics and Water Resources, and best paper award for the paper presented in International Conference on Modeling Tools for Sustainable Water Resource Management held at IIT Hyderabad, and best engineering faculty award in 2017 presented by NIT Warangal and NIT Warangal Alumni Association. And he was the coordinator for TechUp from 15 to 17 and Dean Planning and Development and from 13 to till today 2014. And sir has have vast experience in teaching and research, and of course in administration also. Is a very good academician. Above all, is a very good human being. I am very fortunate that I am the student of Professor N.V.Umamahesh. Sir, thank you, sir, for accepting our invitation and coming despite your busy schedule. And I request, sir, to take over the session, sir.
Hydrological modeling के लिए.
Thank you, Dr. Srinivasulu. It's a pleasure for me to be associated with this program, faculty development program. And it's always a pleasure to share my experiences, and this is where I think there'll be more interaction with different people working in the similar area with similar interests. Maybe it could have been a physical presence that I enjoy more when I come and then present on say offline and then interact physically with everyone. But okay, obviously in last 1 year we are moving towards a new completely new kind of interaction. I think this may become norm for some more time to come. So with this, when Dr. Srinivasulu requested me to give a talk on this, frankly speaking, I told him that I'm not an expert in remote sensing GIS, but I have been using remote sensing GIS in hydrology. I'm basically a water resource engineer with a hydrology background. And so I told him that I'll talk about the applications of this in hydrological modeling. So let me share my presentation. Hope you are able to see my screen.
Yes, sir. Yes, sir. We can see, sir.
Okay. So what I'm going to talk about today is geospatial technologies for hydrological modeling. So as I already mentioned, my focus will be more on hydrology and hydrological modeling. And what is the role of GIS in this hydrological modeling? I think I'll be able to explain that through certain case studies that we have done, using GIS. Okay. So I'll start my talk about hydrological applications. Maybe I don't know what's the background of the participants here. I think I understand that most of you are residents, so you already have a background of hydrology, and maybe you would have studied hydrology. So I can just only give just a glimpse of what is hydrology and hydrological models, and the major applications of hydrological models in like estimating floods or flood forecasting or hydrograph analysis, flood routing. These are the major applications of hydrology that we find in water resources. And then with reference to this, finally, I'll show you case studies that we have done on the application of GIS. One case study that I will talk about is GIS-based decision support system that we developed for watershed management. Another one is the work that we have done recently on floods in Hyderabad city and how to develop the inundation maps in Hyderabad city. Okay. Now, hydrology is something I think all of you would have studied in your undergraduate, or maybe some of you, most of you were faculty, so you know you may be teaching hydrology itself. So, you know, hydrology maybe broadly can be said as a study of water in the natural environment. Which basically we are talking about its occurrence, circulation, distribution, its chemical and physical properties in relation to living things. And obviously, hydrology is a highly multidisciplinary field. In fact, hydrology comes under the sciences. In fact, it's a highly interdisciplinary field in the sense that hydrology needs some knowledge of meteorology, some knowledge of oceanography, geology, and so on, mathematics, and so on. So it's a highly multidisciplinary field. But as civil engineers, we actually focus on engineering hydrology, or what we call as applied hydrology, where we are trying to use the knowledge of hydrology in planning, design, and operation of the water systems, with various types of water systems, whether it's irrigation project or a multi-purpose dam, or maybe a flood forecast system, or even a simple hydro structures like a weir or a barrage across a river. In all these cases, we need the knowledge of hydrology, and so the applied hydrology deals with how to use the knowledge of hydrology that we have in order to solve the problems that we come across in planning, design, and operation of water systems. So typically in engineering hydrology, if you recall, so because all of you are may have studied hydrology, you know that the typical questions that we try to answer by applying hydrology is, for example, what is the maximum probable flood at a given site? Maybe you are designing a huge structure like a dam, a multi-purpose for a project like a dam, and we are interested to know what is the maximum probable flood at that location. Or say you're planning certain activities in a catchment or a river basin or a watershed, and maybe you are interested to know what is the yield from the catchment, and how does the yield from this catchment vary from season to season or from year to year. So obviously, hydrology is a highly in fact, process which is uncertain in terms of knowledge that we have. And so we never will be able to predict exactly what happens in hydrology. So we always have to look at the temporal as well as spatial variation. So maybe we are interested to know what is the yield of a catchment or watershed, or like what is the kind of relation that exists between surface water and the groundwater, especially because these two are the major resources of water resources for us, and many of the locations we'll be using both of them combinedly. So obviously we are interested to know what is the interaction between them, what kind of interaction takes place between the surface water and groundwater. Okay, and then say when we plan projects, say projects like hydropower project, maybe we are interested to know what is the dependable flow. Or say, for example, a water supply project to supply water for a city or town, there also we are interested to know what is the dependable flow. So in such situations, we actually try to evaluate the flow characteristics and then determine the dependable flow, like for example, 90% dependable flow or 75% dependable flow, and so on. And then say, if you're designing a reservoir, what should be the size of the reservoir? What should be the capacity of the reservoir? Or what should be design discharge of hydraulic structure? It could be a culvert across a small stream, or could be a bridge across a river, or could be a weir or a barrage or a dam. Say you're designing that for a separate discharge, and so what should discharge for which you are going to design the structure, or what's the risk of flooding at a particular location, or what kind of hardware or software we needed if you want to develop a real-time flood forecast system. I just listed some of the questions, typical questions that we actually we try to answer when we study hydrology. So these are the purposes for which actually we try to apply the knowledge of hydrology that we have. And that's what actually we do in engineering hydrology, what you call as applied hydrology. So the entire study of hydrology starts with the hydrological cycle, as you all know. This is a typical hydrological cycle, and these are the various processes that take place. So our study of hydrology always starts with precipitation. Precipitation starting point. Okay, and how the precipitation occurs, what are the various modes of precipitation, all these things, though when we teach hydrology, we may talk about that for a little while in the classroom, but basically we are not interested in that. It is completely left to meteorologists. So what we are interested in is what happens once the precipitation takes place. So the precipitation, and then we have from the precipitation, surface water available for runoff. What's the amount of water available on the surface for runoff that takes place here, or what is the amount of water that is infiltrating, and how much water is percolating and joining the groundwater or recharging the groundwater, and what are the other abstractions like transpiration, evaporation, or evapotranspiration, and then maybe we are interested in the quality of water. So what is the chemical constituents of the surface water or the groundwater, and then maybe say there could be interaction between surface water and groundwater. So what is the contribution of groundwater to the surface water, or maybe vis-a-vis what is the contribution of surface water to the groundwater. So these are the various processes that we are interested in studying. And in that process, when we try to study this process, we obviously try to develop some models to understand, to actually simulate this process, and that's how we try to apply that knowledge of this process through mathematical models, and then try to answer the questions that I was talking about in the last slide. So when we are planning, say one of the major applications of hydrology is in planning the various kind of water systems. So why do we need water resource systems? So we have water. Water is available naturally, but unfortunately, water is available at the wrong place, wrong quantity, and wrong time. So what is that we are trying to do now? We are trying to manipulate this hydrological cycle. So we are trying to manipulate the hydrological cycle so that the water that is available in the nature is provided at the required place, in the required quantity, at the required time. So that is what we are trying to do in any water system, whether you're planning a reservoir, whether you're planning a barrage, or you're laying canals, pipelines, and all this, any water resource system that you're talking about. Basically, what we are trying to do here is the water is available in nature. You are trying to say the water is available wrong place, wrong quantity, and wrong time. What you are doing through your system is trying to convert this and make the water available at the right place, at the right quantity, at the right time. Okay, so this is being done by manipulating hydrological cycle, where you're trying to build facilities, reservoirs, canals, flood control systems, and other kinds of infrastructure. Okay, so in this process, one of the applications is, like as I said, one is, for example, you want to flood control the floods, or you want to forecast the flood, or you want to assess the flood risk at a particular location. So this process requires hydrological modeling of floods. So this is hydrological modeling. In fact, I just gave an example of this because the other process also will be, other kind of applications also will be similar to this. So we have the precipitation as input because all the floods are caused because of excess rainfall. So you have precipitation, and you have the various processes take place like interception, deposition, storage, infiltration, which we usually call them as abstractions. And then what is left after the abstraction is what actually comes into the as overland flow, and then joins a channel, a river, and then comes out as a stream flow. To this, maybe we have some other extra additional inputs like from the infiltration or from the groundwater and all these things. And this is combinedly what you call a stream flow, which consists of direct runoff plus base flow. Base flow is the contribution from the groundwater, and direct runoff is what is coming directly from the rainfall event. So we are interested in predicting this so that we'll be able to forecast the flood so well in time. So this is like the forecast here is where you are trying to say predict what is going to happen on a real-time basis after maybe 1 day or 2 days or 3 days lead time. Okay, so now if I want to develop a model for this floods to forecast the floods here, So I need to model all these various components. So all these components like interception, depression storage, evaporation, evapotranspiration, infiltration, and all such things. And another application of hydrology is in design. Like I just now mentioned that we would like to design, for example, a spillway of a dam, or design a bridge across a river, or design a culvert across a stream, or maybe design a stormwater drainage system in urban area. So this is where, say, the hydro design, what we call as hydro design, we try to assess the impact of hydrological event on the water system, and we have to define or we have to choose the appropriate value of the key variable there. Like, for example, you're designing a bridge across a dam or a river, for example, a bridge across a river. Okay, now bridge, what's the purpose of bridge? To allow the traffic across the river even during floods. So now you need to design the bridge for passing out certain, say, to provide some waterway below the bridge, which will allow the maximum discharge likely to occur. So the key variable, that hydrological variable that you are interested there is the discharge. What's the expected discharge? Or let's say spillway of a dam. So again, you have to remove the excess flow that comes during when the reservoir is full. So again, what is the expected maximum discharge that's likely to come? So in hydro design, our aim is to estimate the design variable, which is the discharge there. Or maybe rainfall. In the case of urban drainage systems, we cannot directly know the discharge. So we try to take the design rainfall and then find out what will be the maximum flow that takes place in the storm systems, drainage systems for the rainfall event. So these hydro design is useful for developing plans for a new system, like design of urban stormwater drainage system, design of flood control structures, or maybe it's useful for management plans for better control, like I want to control urban drainage system for controlling the floods in the urban area, or maybe try to map the flood floor areas and identify what are the areas which are likely to have more floods or the vulnerable flood vulnerable areas. So hydro design is useful for either for developing new plans or say develop the management policies for these things. I'm sorry. Another aspect that I would like to mention before I go into the applications of GIS applications in hydrology is the approach with which we try to actually study the hydrology. Maybe this is also something which is fundamental. I think most of you who are teaching hydrology, you may be doing this in the classroom. So when we talk about hydrology in the classroom, hydrology is like most of the time it's considered as a kind of empirical science. If you see till 1980s or 1970s and 1980s, hydrology is purely a kind of empirical science, where it was just observe, measure the various hydrology parameters and develop some kind of empirical relations. So even today, I think some of the government departments, we still depend upon the empirical formula that developed some 100 years back. Like, for example, you say Rice formula, Dickens formula for estimating peak discharge. These are all basically purely empirical expressions which are derived based on some studies and local studies. But the reason why hydrology is a complex subject is, say you have a watershed, say a catchment like this, and rainfall occurs in the catchment, and all this process, the interactions and the say is very, very complex system. Though I may look this problem as a fluid mechanics problem, because it's basically it is a flow. The rainfall occurs in the catchment and there's some water going down, some water flowing down, and I can apply the knowledge of fluid mechanics that we have in order to study all this process, because all this process is only basically involves mass transport in the form of the transport of either the water or its say variants, like moisture, or it involves movement and transport. But the problem is all these interactions that take place here are so complex that it's very difficult for us to apply the knowledge of mechanics or knowledge of physics to actually understand the hydrology and develop the models. So if I can apply the fundamentals of physics, like say the study of movement of water on land, and then develop an approach for studying hydrology, that becomes a physical approach. But that's obviously a right kind of approach for hydrology. But unfortunately, today, with the knowledge that we have about the various processes and the complexity, it's very difficult for us to actually apply all these laws directly and solve them. And that's it. But I need a solution for the problems that I am facing. I need to know maybe is the solution finding what's the discharge here, or find out how much infiltration. So all these things we would like to go for some simplified methods. So that's where we make use of what is called a systems approach. So most of the hydrology is based on this concept of systems approach, where we treat the entire catchment as system. There are certain inputs to the system, and the system, what is, for example, if I take this system here, this is watershed system, the input is a is the precipitation rainfall occurring onto the catchment, and then we are interested to know what is the stream flow coming or flood coming because of rainfall event, and this entire watershed is considered a system. So we are just trying to develop some kind of relation between the output and the input. That's what you call a systems approach. Okay, so physical process and the interactions are at different geometrical scales are not considered directly here. That's what the system approach. We are trying to consider them in abstract way. So what we treat here is a kind of in a mathematical concept where we try to assume that the input is being operated upon by some characteristics or by some function in order to produce the output. And then coming to hydrological models, maybe this is, I think, very relevant when you talk about GIS applications. Hydrological models can be classified into 3 different categories. In fact, I'll say broadly 2 categories. That is, one extreme side you have lumped models. The other side you have what we call as distributed models. Lumped models, what we are trying to do here is all the spatial parameters. In fact, if you consider, for example, I'll just take a simple example. Let's say, for example, you take a small watershed, a small area. And one of the parameters that we are interested in is, for example, say infiltration of the soil, infiltration characteristics. For example, if I'm using a model like a Horton's model for modeling the infiltration in a say location, so the infiltration characteristics of the parameters of the model depend on the soil type of soil. Now, if I take a very small campus, even if I take a small area, like for example, I'll take maybe our campus is say NIT Warangal campus is about 250 acres. If I take these 250 acres of land and then consider this infiltration parameters, I cannot say that infiltration parameters are constant over the entire area that I have. No, imagine this, you are extending for a larger watersheds, a large basins. Can you say most of these parameters, hydrological variables like, for example, soil characteristics or the infiltration characteristics or the other say slope of the land or the rugosity coefficient, any parameter you take up, they're all not constant. They vary from point to point. So if you consider the spatial average of all these things and can assume that entire catchment is made up of one single unit and then lump all the parameters spatially over an area, then we have what we call as lumped models. The other extreme, we have distributed models where we consider that every parameter is distributed over the entire space. So we consider point to point how it varies and then find out how the parameters, hydrological parameters vary over the entire space. Then we have what we call as distributed models. But strictly speaking, say the type of model that we are using or the so-called distributed model that we are using today in hydrology, they're also not exactly distributed. They are semi-distributed in the sense that instead of taking a larger area, you try to lump over small units. Okay, so this is now what is happening here is we are now considering the hydrological parameters as varying with space, not only with time, but also varying with space. So you have to consider the spatial variation. And when you take large basins and you have to deal with a large kind of spatial variation of these parameters, and you need to store the data on a spatial database. And that is where the GIS comes into picture. So the advantage, the advancement of GIS over the last few, maybe 1 or 2 decades, and have made the GIS, in fact, hydrological models more stronger in the sense that we started moving from lumped models to semi-distributed to distributed models because of the usage of these geospatial technologies. Okay. So this is how schematically I'm trying to explain you the difference between a lumped model and a distributed model. For example, I take a river basin like this. This is a river basin. Now, maybe I divide this into broadly. For example, this is one subcatchment, there's another subcatchment, this is another subcatchment, there's output of one subcatchment, there's another subcatchment, and so on. And there's finally the total subcatchment. So if I consider this entire subcatchment as yellow shade area, all the properties, for example, I consider rainfall. Now, can you expect the rainfall to be constant over this entire area? Obviously, no. Rainfall, say even with a small city, say you find that there's a spatial variation of rainfall. You find that rainfall is not constant over the space. It's not uniform over the space. So the rainfall is not constant here. Maybe the soil characteristics are not constant here, or any property you take, they are not all constant. But if I average over the entire area and take the average rainfall, average, the soil characteristics here, and then lump over the entire area, then we refer this as a lumped kind of adversary. Okay. So what happens? This makes our mathematics simple because I'm not considering the spatial variation. For the entire area, I'll take only one value. There's only one rainfall event, or rainfall value, the average rainfall. And similarly, there's only, for example, if I consider the infiltration, there's only one infiltration characteristic and so on. So there's one rainfall runoff model here. And obviously, you will be able to predict the runoff only at one point outlet. And if I want to predict what is the, say, value here, then I had to delineate this catchment, again take the small subcatchment here, and then develop a lumped model for that. But based on the model that we develop for this entire catchment, I'll not be able to find out what is the, predict the values of hydrological variables at some intermediate points in the catchment. The other side, we have what we call as distributed levels. So if this is a river basin, so the same part as, I've taken here in larger scale. So now we divide this into smaller units. Okay. Strictly speaking, I'll not say it's completely distributed model because we're not talking point to point. We're only trying to divide this into number of smaller, say, units like this. Maybe some grids, you use some grids and then try to divide this entire. So each square here that I have here, each square I'll consider as one grid. And within the grid, the rainfall or the other parameters are assumed to be constant, but they may vary from one grid to grid. So that's how you're considering the variation, spatial variation in terms of a gridded model like this. So the advantage that you have here is based on this model, when you can develop a distributed for this, you'll not only be able to predict the outflow at some point here, but you'll be able to predict the outflow, maybe the runoff or other things at some other intermediate points also. So that's the difference between a lumped model and a, say, what you call a distributed model. So now this is where the GIS becomes important for us, the remote sensing GIS, because GIS is, enables us actually to consider the spatial variation. And this is maybe, as you know, because already you have been undergoing this course from last 3 days, this is the 4th day, you already have been, exposed to the various geospatial technologies. And you know, GIS is basically a kind of a huge spatial database system. So that's the advantage that you have here. So you can store all this spatial database and then make your modeling much more easier, distributed models much more easier than what it was before the advent of the GIS and other things, the geospatial technologies. Okay, just to actually quickly maybe introduce the concept of hydrological model. The basic, say, hydrological model start with the continuity equation. The hydrological continuity equation, all of you know, we simply apply the inflow minus outflow is equal to rate of change of mass. So it's a derivation here. So change of storage, rate of change of storage is equal to inflow minus outflow. And for example, if I take a typical watershed, I can say the inflows are the precipitation and runoff coming from surface or from other outside the catchment, or the runoff coming from groundwater from outside the catchment, and the surface outflow and groundwater outflow. These are the outflows. Evapotranspiration, other outflow. So these are the inflows and these are the outflows. Inflow minus outflow. All these are in terms of rates. So that's equal to rate of change of storage. The total balance within the water balance within the catchment is changes with time, and the rate at which it changes time is what you call as GS/T. So this typical equation. All the hydrological models, what the so-called hydrological models, are based on this simple concept of continuity equation. It's called the hydrological continuity equation. ds by dt is equal to inflow minus outflow. The only difference here is inflow as well as outflow are functions of time. They vary with time, and thus the storage also varies with time. Okay, and then I just listed various types of infiltration models that we use. If you look at any hydrological model, you need to have some kind of infiltration model. I just listed some of the popularly used infiltration models and most of the hydrological, software that we have. Like the most simple and common thing is the Horton's model, where you try to express the rate of infiltration as equal to some FC plus F naught minus FC into E to power, sorry, E is missing here. It should be E to power minus KT. I'm sorry for the mistake here. It should be E to power minus KT. So this is, say, what you call as Otter's model, or say Greenhand model, which says the rate of infiltration is equal to Ks plus 1 plus Su by F. This is moisture deficit. IMD talks about initial moisture deficit. Su is soil parameter, what you call soil suction pressure of the soil. F is the cumulative infiltration up to that point. And then other, in fact, I think many models actually try to use this SES model, where this is called curve number, SES curve number method. Though it was proposed for rural catchments, but actually it's more frequently used for urban catchments. And then we have what is called excess rainfall is given by this expression, and where this higher initial abstractions, S is the storage inside in the catchment, and S is given by a dimensionless parameter called curve number, and this curve number depends upon the land use, land characteristics, soil characteristics, and the initial moisture conditions and other parameters. Okay, I think I'm just quickly going through this because you're all familiar with these things. It's only a background that I'm trying to give you, how these things can be transferred and then used in a GIS platform. And then other major model that we use in hydrology is the unit hydrograph model for actually generating flood hydrograph from a rainfall event, excess rainfall event, or an extreme rainfall event. So as you all are aware, unit hydrograph is what you call as a pulse response function of a linear hydrological system. It can be defined as say direct runoff hydrograph produced by 1 centimeter effective rainfall occurring uniformly over a catchment at a uniform rate during a specific period. And basically, the unit hydrograph is based on the assumption that the rainfall over the duration is constant intensity and it's uniformly distributed over the entire drainage area. And then say the system, the catchment behaves like a linear system. Linear system in the sense that a system which follows the say in fact the property of proportionality and property of slope coefficient. I think all of you are aware of this, what the linear system is. So the basic idea behind the unit hydrograph is that the catchment behaves like a linear system, and then that's how, if I know what's the runoff produced by 1 centimeter rainfall, if I want to know what's the runoff produced by 5 centimeter rainfall, I simply multiply that 5 centimeters. Okay, that's what we are trying to do here. That's what. And this is, I think you all are aware, this is how, but if you know the unit hydrograph, this is how we can derive the direct runoff hydrograph from the unit hydrograph. And then here the past data, from the past data, we can always derive the unit hydrograph by what we call as deconvolution. Or we have synthetic methods, especially ungauged catchments. We use synthetic methods to generate the unit hydrograph. In fact, I'll be talking about one of the synthetic methods when I take up the application later for generating the unit hydrograph for a small watershed where there's no gauging data. Okay, one of the methods that is used for deconvolution is what is known as least square method or matrix method of deconvolution. And okay, I'm focusing more on synthetic unit hydrograph because this again where GIS is useful in developing synthetic unit hydrograph, because in the synthetic unit hydrograph, what we're trying to do here is we're trying to relate the parameters of the unit hydrograph, the shape parameters of the unit hydrograph, to various catchment characteristics like length of catchment, shape of the catchment, slope of the catchment, and so on. And maybe most of you are aware of different methods of synthetic unit hydrograph like Snyder's method, Central Water Commission method, SES method. In fact, other method that I'll talk about later is various kinds of, say, what you call conceptual models like Clark model, Nash model, and so on. So this way again to derive a synthetic unit hydrograph, and you need to develop a relation between these unit hydrograph parameters and then the catchment characteristics. And this way again, GIS has played a very important role in developing different methods for constructing synthetic unit hydrograph. And similarly, other area where GIS is useful is in flood routing. And maybe again, those who are familiar with hydrology, you know, flood routing is a process where you're trying to study the propagation of flood through a, say, river. Okay. Again, if you actually consider propagation of flood in a river, it's supposed to be a kind of an open channel flow, unsteady non-uniform flow. And you can try to develop this as one-dimensional model or two-dimensional model or 1D, 2D coupled models. And if you really consider, say, as an open channel flow, and apply the basic laws of channel say flows, so free surface flows of unsteady non-uniform flow. I think most of you are familiar with this continuity equation, and this is the momentum equation. These two together we refer them as Saint Venant's equation. So if I want to study the propagation of flood through a river, I need to solve these two equations. These are two partial differential equations, and there are different methods, numerical methods available for solving this kind of partial differential equations. The problem in the case of hydrology, if I want to apply the flood routing to a natural river system, then getting data to apply this model is very, very, very difficult. It's almost impossible. So in hydrology, we never use this kind of model. Maybe in urban catchment, we may use this kind of model because there the channels are the man-made channels, and you can know the characteristics of the channels completely. But a river is a natural channel, and knowing the characteristic of the river channel is very difficult, maybe in a distributed way. So the reason why we go for simplified models like, for example, kinetic wave model, diffusion wave model, dynamic wave model, and so on. And in fact, I just mentioned about this kinetic wave model, which is one of the commonly used model. Again, in most of hydrologic models, they depend on kinetic wave model, where you are simplifying the momentum equation by writing S naught is equal to SF by neglecting certain terms in the momentum equation. And this is a simplified equation that you have by combining the continuity equation and momentum equation. And then we try to solve this equation numerically by using finite differential. So most of the hydrological models, the distributed hydrology models, which are developed on the platform of GIS, actually use this as a very common method of flood routing, especially models like, which I'm going to talk about later, like stormwater management, water stream, or SWAT and such other models. Okay, and say other simplified method of flood routing is what you call as hydrologic flood routing, which depends on the hydrologic continuity equation, which is where you are trying to write I minus T, and then along with that use a storage equation called Muskino storage equation, and then by combining these two equations, we can develop a simple procedure like this to route the flood. And this is something which I think many of you know in hydrology. The only thing is here, I need to know the parameters K index. So how to estimate the parameters K index is again a big task, a big challenge, and there are a lot of methods for estimating K index, and that's what is inbuilt in most of the hydrological models. So with this, all the background about hydrological modeling, let us now look at the role of GIS in, say, hydrological modeling. Okay. Now, as I was mentioning, till about few decades back, maybe up to 1980s or 70s, hydrology was purely an empirical science. The reason is, say, the hydrological models that I've been talking about require huge amount of data, information, and processing that information was difficult those days because of lack of computation facilities and lack of this kind of database systems like the type of that you have from GIS now. And maybe remote sensing also was not that developed for those days. This is why people depend only on simple point-to-point observations and then try to develop some models. But with the advent of the computer facilities and computation facilities, I think today hydrology model has become, say, more, better, and then where we try to incorporate the spatial heterogeneity, especially most of the catchments, they are not spatially homogeneous. And so this spatial heterogeneity can be incorporated by say, using the GIS. So this GIS is useful in estimating hydrology parameters, hydrology modeling with in the GIS platform, or maybe we can have some features where you can couple a GIS with hydrology model, like what most of the modern day, hydrology models try to do it. Okay. So I'll just first try to demonstrate a simple hydrology model, which is useful for a small catchment, especially a small catchment where you don't have any kind of data, no flow data. How we can make use of GIS in order to say maybe take up some activities in the say catchment, like for example, many of you are aware of watershed management activities that I think government has taken up in a large scale about 1 decade back or 15 years back for both basically for soil conservation as well as water conservation, water harvesting and others. So during that time, we are involved in developing a decision support system for watershed management. And we have taken one of the mandals in Warangal district, no, okay, this is the Warangal districts as well, but in the after I think in the last 5 years back, districts have been demarcated. So maybe this now is no longer, I think, in Warangal district. Is the districts' names have changed, but I'm talking about the United Warangal district that we had before 2014. So this is what we call as a Ganpur mandal, and we have taken some catchments here. We try to. Our aim was to develop because a lot of watershed activities, watershed management activities were being taken up. And we want to develop a GIS-based decision support system to help the decision makers in identifying the activities to be taken up in the watershed. So maybe I just try to explain to you how the GIS was useful in developing this kind of support system, and maybe that's a kind of case study that will help actually any kind of hydrology models also. So this is a typical flow chart of what we did. So obviously we need spatial data in terms of topo maps. We have collected the Survey of India topo maps and the socioeconomic data because most of the watershed activities require say involvement of the say villages there, and then other kind of collateral data. And all this we created a GIS, a database in the GIS. Okay, in terms of where the GIS will have will have a database of the various water bodies, the drainage network, and the digital relation model layers. And then we also try to process the digital, say, remote sense data. And then using image processing, we developed the contour layers as well as the land use layers, land use curves. And all this are analyzed now in the GIS platform. And the various hydrological modules that we developed for based on the GIS analysis is the stream ordering layer, the hydrological soil, say group the soils, and then slope, land use layer, curve number. These are the parameters of hydrology. And then based on that, we have an hydrology model which helps us to find out what is the hydrograph produced because of rainfall event. And then that will, in turn, we use that in order to identify the sites or select a site, suitable site for say structures like check dams or farm ponds and other such kind of water harvesting structures. And then other important aspect that happens in say that we are interested in studying is the soil erosion. So we have a soil erosion model which will predict the soil erosion based on this GIS analysis. And then based on that, now we'll identify what are the areas which have significant soil erosion or severe soil erosion. And then we need to prioritize them. And then we develop a fuzzy-based module for say identifying sites for controlling the soil erosion process, soil erosion or control of soil erosion. So I'll try to just very briefly explain with the time limits that I have. I just try to explain some of these modules and how the GIS was useful in making the hydrological model easier. Okay, this is the hydrology model because our focus is hydrological modeling. This is hydrology model. And so the inputs that we have taken are again drainage network, the say elevation network, the rainfall map. We took the rainfall data and then used that based on that analyze the spatial variation of rainfall, and then we obtain the remote sense data, and then try from that we try to get the slope characteristics and then the land use characteristics, and created a digital elevation model, and then identified the various water bodies. And now we use different types of hydrological models in order to develop the hydrological model. So basically, the hydrological model, the purpose of hydrological model is given a rainfall event, we would like to know how much is now produced by rainfall event. So we use from this unit hydrograph theory, but this is an ungaged catchment, so we don't have past data so that we can develop based on past data what is unit hydrograph. So we need to obviously depend upon synthetic unit hydrograph. So we use this module contains the various methods of synthetic unit hydrograph. Now, which of these methods is suitable for that particular location is depends on the user, like knowledge about the catchment. But we can use one of these models like Clark's model, SES model, or what you call as geomorphological instruments unit hydrograph model, or Central Water Commission models. So these are the various models that we try to use in order to develop the synthetic unit hydrograph. And then, given the rainfall and the synthetic unit hydrograph, this module will estimate what is the runoff coming. So this is say how this is a drainage network of the say the Kerala watershed. Now maybe you already would have been, I don't know if we had some kind of hands-on experience during this course, or some of you are already familiar with the GIS. Say, when you are given some, say, a catchment like this, now GIS helps us for basically first to delineate the catchment. So even the delineation of catchment can be done by from the say GIS based on the contour map, and then based on the flow, say the slope, and then flow, we identify the flow grid, flow paths, and based on flow paths, this entire drainage work actually can be generated and compared with actually what we get from the topographies. So the GIS can help us, in fact, actually generate this entire drainage network also based on the say the contour map, and then the say topography that we have. Okay, so this is a drainage map that we have, and then say, in fact, if you want to really study the morphology of this area, like for example, what is the stream order, and then what is the length of streams, and then what is the length of first order streams, second order streams, third order streams, and so on, and what's the total water spread area of the water bodies, all these things is easy to obtain from a GIS. I think these are things that maybe you are learning in the part of this course. Okay, and this is the digital elevation model that we have created for that catchment. Please note that it's a very small catchment, a small watershed, because all these watershed activities are taken up in small watersheds. And this is how the elevation. It's not a, in fact, we find that so there's almost 200 meters elevation difference, and so slopes are significant. And this, say, is clear indication that this kind of areas are prone for erosion because you have steep slopes, in fact, high slopes here. Okay, and this is the land use land cover map, and as you can see here, in fact, most of the area is mostly a kind of barren land with a lot of shrubbery. Okay, this is all mostly shrubbery, and you have these are the these orange color. These things are all build-up areas, which sorry, these are all agricultural lands. So you find that it's not predominantly agricultural land because there were no irrigation facilities. You find that agriculture was available only along the sides of streams. So they try to divert the water, and then only along these places you find only some points. So aim, in fact, one of the objectives of this watershed development is to actually increase this agricultural activity, or increase the agricultural land, because it's basically a rural watershed, and then increase the area of under the agriculture. And then we have other kind of, like, for example, this part forest areas, they have basically it's okay. Some areas which are having forest cover, and then we have water bodies, and then in fact a few, but there are not many villages here, small villages only. So you won't find built-up areas unless I analyze this. It's very difficult to identify the built-up area, but some of these locations you have villages where you have some kind of built-up area. Otherwise, it's not a kind of urbanized area. There's no urbanization here, so there's no much major built-up area here. Okay. In fact, the reason why we have taken this as one of the case studies here is because large area is just simply shrubbery or barren land, and maybe one of the activities of watershed is to actually go for water harvesting and try to improve the water availability so that it can be brought into agriculture. And one of the methods that we use to estimate the runoff is, like as I mentioned earlier, this SES method. Again, I'm not going to the SES method, but I'll just show how this SES method can be modeled in hydrology.
इसका चला गया है क्या इंटरनेट?
Hello?
Okay,
Hello?
sir.
Okay. Yeah, I thought somebody is asking a question. Okay, I'm sorry. Yeah. So basically, say, in fact, here, this is the curve number is the most important parameter in this method of estimating the runoff. So now the curve number, in fact, if I have not used the GIS platform, if I let's do like normally, maybe one way is to take the average curve number over the entire area. But the advantage that I have here is I can now actually go for say divide this catchment to small grids, or in fact, the method that we have used here is a not complete distributed kind of model. What we did here is, now we have different types of land use. The curve number depends upon the type of land use that you have. For example, agricultural lands, you have, say, maybe I can identify what's the cover number here. Okay, based on the agricultural land and the soil characteristics. So the barren land will have a different cover number. So now we use one cover number for all the agricultural lands, one cover number for all the barren rocky lands, and one cover number for forest land, and so on. And thus we'll have different cover numbers for different areas. So I know how much is agricultural area. So that area will have a cover number of some CM1. And similarly, if I know the forest area, total area of forest area, for that is say other cover. Now, what we did here is a kind of only a lumped model only, but only not say in the lumped model, instead of taking a simple average cover number, what we did here is a kind of weighted cover. That means we took the weight as the area of the say of particular cover number. So agricultural land will have some cover number, then barren land will have some cover number. So each of that we try to identify the cover number and then take a weighted average like this. So and then substitute here. So this is basically, I would say it's a kind of distributed model. It's a kind of lumped model. The only thing is we are trying to use the spatial distribution in order to improve the lumped estimate of the curve. That's the only thing that's the advantage that this has in compared to a typical lumped model that we normally use. Okay, this method for how to we estimate the curve number based on this, like we got all the data, soil data, land use one curve map, and then topological map, and then after digitizing this, we for each of these groups we try to identify what's the curve number, and then simply overlay them and then identify the curve number. Say this is how the curve number grid looks like. This is the curve number different for different parts of the catchment. So this like red lines, this part wherever it is red, this is 58, and now we have water bodies. Obviously, curve number is 100. So this is what we have 100. And like this, for example, these areas, green areas, the curve number is very high, 92, and so on. So based on this, now we look at weightage. Okay. And then, in fact, I can also use this curve number distribution and then substitute this into this model and then estimate the runoff and thus create what you call as a runoff grid number, grid map, which will indicate what will type of runoff that in centimeters that is expected to come at different locations. So this will help us to know how much is the runoff at different locations, how much say from the rainfall, given rainfall, what's the runoff at different locations. And then it will be useful when you are planning some kind of activity, like, for example, water harvesting structure or soil erosion, say a structure to control soil erosion. So this map will help us to identify where the runoff is more and where the runoff is less, and then accordingly, identify how much is, say, for example, if I plan a check dam at some location, how much is the runoff expected at the location? I think this spatial distribution runoff will help us to identify that locations. Okay, this is another method of estimating the say instantaneous unit autograph or synthetic unit autograph, what is known as geomorphological instantaneous unit autograph. This is the method which uses some geomorphological parameters like say for example the characteristic of the catchment, length of the catchment, velocity of flow, and such things, which we can easily obtain from, like for example, area ratio, bifurcation ratio, basin circularity ratio. It's all what we call as morphological parameters, which say can be easily obtained from say a GIS map. So if you create a distance your catchment and then computing these values becomes very easy, and thus computing this time to peak and QP, the peak to peak discharge, and then thus constructing this synthetic instantaneous unit autograph becomes very easy. So that's the advantage that we had here as far as GIS is concerned. So we have used GIS in order to estimate all these parameters and morphological parameters, and then based on that construct this geomorphological instantaneous unit. And then other method of constructing the synthetic unit autograph is what is known as Clark's model. Say maybe again those who are familiar with hydrology, you know this is a kind of conceptual model. What the Clark's model assumes is say the entire catchment is made up of into two parts. One is what you call as a linear channel, and then a linear reservoir. So linear channel is modeled by using what is known as time area histogram. Now, time area histogram is a histogram that you plot where you plot, say, against time, the area, say, area having, say, time of conservation equal to certain time. So, say, different parts of the catchment will have different time, area of travel to the outlet. So, based on that, we plot how the area is distributed over time of travel, and that's what we call as time area histogram in the form of bar chart. So, time area histogram is, like I'll say, is kind of input to the Clark's model. And then, say, based on that, we try to route this time area histogram through what you call a linear reservoir. Okay, and thus is the output. The output from the linear reservoir is what you call as a Clark's instantaneous unit area graph. Okay. So the parameters that you require here are the time of concentration. As you all know, what is the time of concentration? Is the time of travel, the largest time of travel, or the time of travel from the farthest point in the catchment to the outlet. And to get the time area histogram, I need to find out the time of travel from different points in the catchment, and then based on that, map them and then develop a time area histogram. And then, say, farthest, say, there's a linear reservoir, we need to find out what is the storage coefficient K. So, a linear reservoir is a reservoir where the outflow in the, say, from the reservoir is, sorry, storage in the reservoir is directly proportional to Q. So, S is equal to K into Q. So, that's what you call a linear reservoir. And the K is, say, what you call a storage attenuation coefficient. So that's another parameter of the Clark's IUH. So this is a process that we can use in order to, say, obtain the synthetic unit graph by Clark's method from say, using GIS. So the basic input that we have taken is a distillation model. And based on distillation model, you can plot the flow, say, flow direction grids. And from the flow direction grids, we'll try to, say, find out, say, this process, we find the flow length, and then we'll find out version flow length, and then the characteristic of soil or land use and all those things. We'll try to find out what is the time of travel from that grid, and then say, combine all these things in order to find out for every grid point, what's the time of travel to the outlet. And then when you plot this time of, say, this area of grids with the time of travel, this is what you call as time area histogram. So this time area histogram can be easily obtained. Okay, here, in fact, in the GIS, we are actually computing the cells, and that cells, if I each grid cells I know, and then I know the scale, I can convert into area. And this is what we call as a time area histogram. And then this time area histogram is actually routed through, we actually try to, this histogram will try to convert into a, say, a continuous curve by what we call as translation hydrograph. And then this translation hydrograph is routed through a channel and to obtain what is called as routed through a reservoir, for a linear reservoir, in order to obtain the instantaneous unit. Okay. This process is not, say, where maybe it's a typical hydrology model. Okay, I already talked about routing and then how to route the flood and all such things. So the basic use of GIS is the same. So if you have the digital elevation model, then computing time area histogram becomes very easy. And once you got a time area histogram, and then from that obtaining translation hydrograph and then say routing it through a linear reservoir is all a simple hydrological model, hydrological process. So this is how it's say this GIS is useful in constructing the unit graph using Clark's model. And okay, this is just a result that we obtained for one of the catchments, sub-catchments of that area that we have taken up for study. So we got the IUH, and from the IUH we obtained the 1 hour unit area coordinates. Okay. Now, whatever I discussed now, in fact, strictly speaking, they're all lumped models which are used for, say, in a form which is basically, I'll say, I try to use a distributed platform like GIS, but to develop a lumped model. Obviously, I'm not practically using all the characteristics of a distributed model there. It is basically what the model that we have used there in the earlier example that I've shown are completely what you call as lumped models. The only difference here is to obtain the parameters for the lumped models. I use the GIS as a platform and then aggregated the spatial variation. So that's what we did there. But let me take up an example of a purely distributed hydrological model. Okay. So a distributed hydrological model is a model which accounts for spatial variability of, like all parameters like precipitation, terrain, soils, vegetation, land use, channel shape. All these have high spatial variability. So any model which accounts for the spatial variability of all these parameters is what you call as a distributed hydrological model. So in the earlier example, what we did is, though they are distributed, we just consider the distribution and from that you average it and then use the average values only in the model. So it's basically what we use is a lumped model. But if I consider this variation, incorporated spatial variation inside the model itself, then we have what you call as distributed hydrological. Okay, I just repeated the same slide that we usually explain what is the difference between lumped model and say a distributed model. So let me, in fact, I think some of you are working in hydrology would have already used some of these models. These are all examples of either what you call as distributed or semi-distributed. In fact, most of the models I'll say they're not strictly distributed, they're semi-distributed models. Like one of the very popularly used hydrological model today is soil and water assessment tool, or what you call a SWAT, or the other one is called variable infiltration capacity model, VAC model, watershed simulation and forecast system, WSFS, that's what is known as. It's another model. Soil and water integrated model, watershed modeling system, stormwater management model, precipitation modeling system. So this are all some of the examples of either distributed or semi-distributed models. In fact, some of these models are open source software, so they are easily freely available, and we can use the SWAT, VAC, or the stormwater management model that we use in urban areas, even PRMS. These are all free software, I think, and that's the reason why they have become more popular and people are using these models for hydrological modeling. I just give an example of one of such models, one of the distributed models, what we call as variable infiltration capacity model. So as you can see here, so this model is developed by, say, an university in US. And so typically you can see this is a grid. Okay, in the grid, we consider all the energy and moisture fluxes. There's rainfall, and then there's some infiltration going down. And then we, because it considers multiple layers of, say, soil, and then assumes that the infiltration rate depends on, say, varies with depth here. That's the reason why it's known as variable infiltration capacity model. These are the different types of soil layers, 0, 1, 2, and so on. And there's a top canopy, the vegetation cover or the canopy cover that you have. And what are the various fluxes that are taking place? There are energy fluxes which influence the hydrological cycle, like solar radiation received or reflected back and all these things. And then similarly, there are moisture fluxes in terms of precipitation, evaporation, evapotranspiration, or say infiltration, runoff, base flow, and so on. So for each grid, say all these fluxes are considered. So there's all these fluxes are modeled, and then grid-wise they are modeled, and we consider multiple layers like this. And then each layer we consider all these fluxes, and then based on that, we try to develop a model for, say, runoff. We try to compute runoff from each grid. So the output from this analysis of this each grid is runoff coming from the grid, and also what's the base flow coming from the grid. So runoff and this groundwater contribution to the surface flow. That is, both these are the outputs of this for each grid. But now a catchment is made of number of grids. So this now for each grid we are getting the runoff coming from the grid. And now this, say, runoff from each grid is routed using another module, routing model. And then finally, what we get as outlet is the flow that is routed. So this is, I'll say, a distributed model, in the sense that because you see each grid, now you consider the characteristics of each grid separately. So every grid, in fact, you can make it as distributed as possible by taking this as small grids as possible. So if you take a very small grid, and each grid, the characteristics may be different, the parameters may be different. So that's how you are making it a truly, say, distributed model. So this is a model, in fact, which is recommended for, in fact, studies on impact of climate change, because I think a lot of interest is there on studying the impact of climate change in hydrology. And say a lot of people use different models. So one of these models is this VAC. In fact, in one of our studies, we use these models. in order to study the impact of the climate change on some of the subbasins of other basins. So we use the VAC model. Because the advantage that you have VAC model is because you are using all this energy fluxes and the moisture fluxes, integrating this with climate models is much more easier than other hydrologic models. That's the advantage that this VAC model has. Okay. Just this is an example of one of the distributed model, but I can go on talking about different types of distributed model that we have, like SWAD, SWIM, and so on. But now, using this concept distributed model, I'll just show another example of how we made use of GIS, so geospatial technologies, in order to model the floods in Hyderabad city, the urban floods in Hyderabad city. Okay. Now, the first thing that we have taken up is like how the land use pattern in the Hyderabad city is changing. Okay. So this is, we use the remote sense data from 1972 onwards up to 2013 and process that and try to develop the land use maps for this. And in this red shaded portion is the urban area. So this is 1972, the map of 1972. So in 1972, Hyderabad was only this much area. Okay, this area. You see how from here it started increasing. So developing 1972, this is 81, this is 89, this is 94, and this is 2006, and so on. This is 2013. So you especially from this E is I think somewhere in if I remember correctly, this is I think 2000, somewhere in 1999, 2001. So from here you see that expansion is almost exponential. Okay, so the city, this is something which is very important from hydrological point of view because the land use has a significant impact on the hydrology of a catchment. So you have a rapid urbanization taking place here, especially from this period onwards, from 2000 onwards, maybe from 2000 or 1994 onwards, there's a rapid expansion of the urbanization. You can see when I plot the urban area, built up area against time, this is the graph that we obtained. You see, this expansion has been very significant over this part. Okay. If someone is interested, know how actually we did this processing and then obtained this, I think that we can refer to our paper that we published in Journal of Hydrology in 2015. Okay, so this is how what's the implication of this? Maybe this, because like time I know this out of scope for this talk today, but one of the important implication of this entire process of urbanization is the increase in rainfall, extreme rainfall. In fact, there's a study that this student of mine who has done his PhD under my guidance. In fact, he has done a lot of extensive study on how this urbanization and other local variations as well global changes, climate change, are impacting the extreme rainfall in Hyderabad city, and that's the reason why Hyderabad is facing more frequent floods in the recent times. Okay, anyway, I'm not going to details of that study, but this urbanization is causing more of floods. So one of the topics that other study that we have taken up is to model the floods in the Hyderabad zone, Hyderabad region. And this is a complete Hyderabad map of the Hyderabad city, what is known as GHMC, Greater Hyderabad Municipal Corporation. This is the total area of the Greater Hyderabad Municipal Corporation. And they divide this entire thing in based on hydrologic characteristic. The GHMC has divided this entire Hyderabad city into number of zones. And based on discussion that we had with them, they were more concerned with the floods in zone 13. This is zone 13. This is zone 12, which are predominantly very highly developed, highly dense areas, dense in terms of population and built-up areas. These are like, for example, they all join Hussain Sagar. So this is Begumpet, Kukatpalli, all these areas. If someone familiar with Hyderabad, they know these are very high densely populated areas. Okay, so these two zones plus this zone, which is basically a what you call as old city area. These are three zones that we have taken up, but I'll just try to show about this 12th and 13th zone, how we actually use the GIS platform, hydrologic models, GIS, in order to develop the flood inundation maps and for the city with these two zones. Okay. Now, this is the land use map for a particular zone. So this is, I think, for zone say 12. Okay, you can see the total area is 143 square kilometers. If you look at the built-up area, it was 65.18 in 2001 and has increased to 84.29 at the cost of water bodies, because a lot of water bodies have been encroached upon. If you see the say most of the water bodies have started shrinking when you come from this to this area, and then in fact shrub area and the barren land, all these things have decreased, and then built-up area has increased. And this is how, like, what happened, 46 to 59%. That's how the built-up area has increased. And this is for other zone. Again, we use the remote sense data and then data land use analysis. And then say this yellow shade area is the built-up area. So again, you see how it has increased from 28.88 square kilometers to 35.44. The total area is only 47. So now predominantly it has become more of built-up area. Built-up area has become very, very large here. Okay. And then you find again the water bodies have shrunk. And this is the statistic, 62% to 75%. That's increase.
Sir. Hello. Hello.
Hello.
Hello.
Sir. Yes, sir.
Yeah, I think some disturbance was there for some time. So now I'm audible?
Yeah, you are audible, sir.
Yes, sir. Sir, one question, sir. The whatever data you have shown, the watershed area has increased. If you go to the previous slide,
Yeah.
0.64 to 0.70.
Yes, okay, this I think maybe could be a kind of, because as I said, this could be, in fact, if you see, actually it shows as 1 to 2%. In fact, water body here, okay, this is, in fact, it was 1%, 2%. Okay, strictly speaking, I think water body, because very, very small, this could be a kind of, I'm sorry, this could be sometimes, because what we did is we got the remote sense data and then we use the image processing in order to actually obtain this. And that image processing process itself is erroneous. There could be uncertainty. And so there could be some errors in the actual area that we compute. So the actual area could be different.
That may be. But the shrubs has also increased.
These are all small areas. So when you try to project the small areas, there could be some kind of error in the processing itself, because say the image processing from remote sense data and then trying to obtain the land use pattern, I think there are different methods, and the accuracy of your results depends upon the type of method that you have and then the process that you use. So there's always some kind of error in the processing, because basically what you're trying to do is some kind of statistical analysis, and any statistical analysis, there's always going to be an error. So maybe that's could be the reason why there's small variations in this this thing. Because what actually basically, if you go to the field and observe, it's basically the barren lands which are being built up. So the barren land has considerably decreased, and whatever barren land addition is taking place, that has become built area. These things, there's not very significant change, and these changes that you are observing between these two areas is only maybe some kind of a calculation mistake or error in the processing of the image remote sense data.
Okay, thank you.
So we use here another open source software for hydrology modeling, which is called HEC-HMS. It's called HEC-HMS. HEC is the name of the organization. It's a Hydrological Engineers Corps. This is an organization in the US, and they have different types of, there are different various models. And one of the models for hydrology is Hydrological Modeling System. HEC-HMS is Hydrology Modeling System. So we made use of this hydrology modeling system. This entire HEC-HMS works on the GIS platform. So it's a GIS-based, model, hydrological model. In fact, it's called GeoHMS. In fact, I think I should have used the term HEC-HMS was earlier model. What is being used today is HEC-GeoHMS, where it's the GIS to incorporate the GIS. It's entirely built on GIS. So we have the inputs are the basin parameters like infiltration parameter, drainage details, and rainfall data from says another input, hydrological input, and then to simulate maybe the simulation parameters like the time step for running the simulation and other control parameters are specified. And then we run this HHS model and we produce the hydrographs at different junctions or different reaches or different subcatchments depending upon where you're interested. So we try to, I just show you how we generated the hydrographs at different junctions of the drainage networks. Okay. I'm sorry, I think that was missing. Yeah. Okay, I'm sorry, I think the graph is missing. In fact, I thought I have included the graph. So we try to generate the say hydrographs at different junctions and different reaches, and that was given as input to another model, what we call as HEC-RAS. HEC-RAS is another open source software. This is again developed by Hydrological Engineering Corps organization. It's called River Assessment System. RAS represents RAS. It's a hydrodynamic model which actually does the hydrodynamic modeling of river basins. In fact, basically HEC-RAS is more useful has been more widely used in developing the flood generation maps in river basins. But what we thought is maybe we can make use of an urban area also, and that's how we try to use this HEC-RAS in urban area. Again, this is, as you can see here, it's again a model which is built on GIS. So this takes inputs from the HHMS. So we try to simulate this HEC-RAS model for 3 different rainfall events, which was severe rainfall events that occurred in the past. One was the July 1989, there was 199.3 millimeters in just 33 hours. And then August 2008, there was a rainfall of 220.7 millimeters in 36 hours. And August 2000 is considered as other weather major rainfall event, 312.1 millimeters in 31 hours. Now, all these 3 rainfall events were considered as one of the very severe rainfall events. I think the recent in August 2020, October 2020, I think the rainfall was much more higher than this or almost on par with this, which caused a large flooding in many areas. I think many of you have read in newspapers, or some of you maybe from Hyderabad, last October, we had a very severe extreme rainfall in Hyderabad. But these are 3 major rainfall events like in the past. We try to simulate and then develop the flood risk or flood inundation maps for these 3 events. So this is a process. Say, for example, again, you need a spatial data, which we try to process and then store in ArcGIS. We use ArcGIS here. So we get both spatial data as a measured data, like measured data in terms of rainfall or runoff if you have measured, or the the drainage characteristic based on the measurements that are on the field. And then this was given to GeoHMS model. And then based on GeoHMS model, we did the rainfall modeling in that. And then we get the output stream flow hydrographs at different points along this thing. And this is given as input to the HEC-RAS model, which is a combination of 1D, 2D hydraulic model. One-dimensional, it uses a one-dimensional model, like the type of state finance equation that I showed earlier, or kinetic wave model that I showed earlier is used here in order to model the flow in the channels. Whereas the flow over the land is modeled as a 2-dimensional flow. So when in an urban area, when a flood occurs, we have both 1-dimensional and 2-dimensional flow. When there's no flood, all the water flows into the drain and then flows in the drain. That's basically a 1-dimensional flow. But once the drains become full because of excess rainfall and they start overflowing, then you have surface flow also. So obviously surface flow cannot be modeled as 1-dimensional. So you need to club with a 2-dimensional flow. So HEC-RAS is uses a combination of 1D and 2D. It's a 1D, 2D hydraulic model. So we have both the models. HEC-RAS 1D is used for modeling the flow in the channels, and HEC-RAS 2D is used to model the flow on the terrain. Okay, and then based on this combination of these 2 models, we will be able to generate floodplain maps, or the flood maps where the flooding can take place. Okay. So this is how, for example, this is a digital terrain model that we generate using digital elevation model. We develop the digital terrain model, and then this digital terrain model is discretized into a two-dimensional flow area. So that this is given as input for the our HECRAS model in order to generate the flooding over different areas here in this area, this particular area. Okay. This is how we can actually see generate the flood maps over time. So, for example, this is 1989 event, rainfall event. So, as time progresses, you can see this blue shade areas are the areas which are getting flooded. The flow starts accumulating, and this is how the flooding propagates. For example, this is starting, and as the time progresses, you can see by the end of this rainfall event, you find these are all the areas which got flooded. So, this is the 2000 event, and this is the 2008 event. So you see how, in fact, this say through this GIS, we are able to visualize how these flood can propagate. In fact, we can generate a kind of a simulation, on time, and then create a video like to show how the flood starts propagating and spreading over the areas. So this is now I can try to identify what are the areas which are getting flooded here, and maybe the HECRAS also gives me what's the depth of flow at these locations, what's the depth of inundation at these locations, and what's the velocity of flow at these locations. These two, are most important when you talk about the flood vulnerability. As the depth increases, maybe the area, the damage caused by the flood becomes more. So depth is one of the important parameters. And if the flow is high velocity, that can cause damage to even vehicles moving properties, or can wash down people or vehicles and all those things. So velocity and depth together, based on that, in fact, there are indices which can find out towards the flood vulnerability or flood risk. And that's what we can generate that kind of maps using these maps here, because now what's the depth of flow at different locations and what's the velocity at different locations. And this is how I can actually finally map all these things, and then maybe overlay on say Google map. So, for example, in one of the this thing in zone 12 and zone 13, these are zone 12 and zone 13. You can see we overlaid this on the Google Earth maps, and you can easily identify what are the localities which are prone for flooding. Dark blue are more severely flooded, whereas light blue is areas which are less severely flooded. So you can see all the areas which are getting flooded here. So these are locations which are getting flooded, and this is how we can actually develop a flood inundation map. It will be useful for the people who are on the field and try to help them, reach out to people who are affected by flood and then take precaution measures. Okay. So in summary, I'll say geospatial technologies have evolved. Maybe they have become now very sophisticated data management systems. Over the year, especially last, I think 1 or 2 decades, there are a lot of developments which have taken place in this remote sensing and GIS, and this geospatial technologies have become, very sophisticated in sense. So we can actually store a large amount of, hydrological data, which is useful for analysis. And then both remote sensing and GIS together can provide a lot of information. Like, for example, the example that I've shown in urban area. In fact, I just showed about only flood inundation map. But if I can map from I can try to get the data from other sources, like, for example, the property, buildings, the property, or what kind of land use we have there, and then that also will help me to actually generate more information, and then help us to actually manage the flooding scenarios at those locations. But okay, in spite of all these these things, I think there are several challenges. See, basically, okay, today we are using a GIS as a just kind of platform on which you are building a hydrology model. But I think there's more need for integrating them into a single platform. In fact, remote sensing, GIS, and hydrology together actually can do much more than what they are doing today. In fact, I'll say, for example, let's consider the problem of real-time flood forecasting. Okay, I talked about only flood inundation maps, which we use GIS to generate flood inundation maps. But what is more important, what will be more useful for a city like Hyderabad is a real-time forecasting, where I can, on a real-time basis, if I can make a forecast at least 2 hours or 3 hours ahead, and that these are the areas which are going to get flooded. Or let's say, for example, a river basin, if I can do in 1 day or 2 days lead with lead time, I can forecast a flood in maybe a river basin. That will help in say taking measures to mitigate or reduce the damage, minimize the damage caused because of floods. So for this, I think we need to do much more. Say, especially, for example, we need to integrate the GIS or remote sensing with various other kinds of tools that we use for collecting data. For example, you take an urban area. I can try to say we can try to install sensors which will try to measure the rainfall. We have, for example, you can install automated weather stations which will continuously monitor rainfall, and then say it's collected at some point. And then we also have data coming from different drainage networks on the water levels in that. And then if you can integrate that with the GIS platform into a hydrological model, then the hydrological model can run on the real-time basis, and then would be able to predict what happens next 1 hour or what happens next 2 hours, and then based on that, we'll be able to tell these are the areas which are getting flooded. So to this now, if we can integrate the weather forecasting system, say we have now a lot of sophisticated or lot of improvement in the weather forecasting. So maybe say some of these areas, I think urban areas, I think we're able to forecast weather 3 or 4 hours ahead at least. I think in Hyderabad recent October rainfall, I think 1 day ahead itself, the IMD has given a forecast that there will be going to be severe rainfall in the city of Hyderabad. So if you can incorporate this to this platform where you have other source of information, all these are integrated on a GIS platform, and then we can actually make our flood forecast system much more better, and then on the real-time basis, it will be very, very useful for the society. The same thing I can extend to a river basin also. So what we need is how to integrate this, say, various sources, and then integrate them with the hydrological models, and then make them more useful. And this is, I think, where I think we need a lot of things to be done. And there's a lot of challenges. And this is where I think most of the young researchers who are working in this area in hydrological modeling or GIS, I think they need to come out with solutions for this and come out with new technologies which can integrate all these various sources. So with this, I conclude my talk. So if there are any questions, I think I'm ready to take any questions.
Very good afternoon, sir.
Yeah, good afternoon.
I'm Ravi Kumar, sir, from JNTU, Hyderabad, sir. Sir, there are a lot of models available, sir. You have used the HECRAS and HMS.
Yeah.
In the 3 divisions of Hyderabad.
Can you just speak louder? But I'm not able to hear you.
Sorry, sir.
Yeah.
You have used HECRAS and HMS, sir.
Yeah,
and you have shown the area-wise, sir, how flood is spreading.
That's, yeah.
Sir, can we, with the help of these models or any other models, can we identify the depth of the flow, sir? Because along the Musi River only, a lot of flood has, damaged buildings and spread over area. So can we predict? Can we able to?
Yeah, that's what. In fact,
depth of water, sir.
Yeah, definitely. See, in fact, because of time limitation, and in fact, this is a part of a study that one of my students has taken up, who just recently completed his PhD. In fact, his final outcome is like a flood risk, which talks about depth of flow, because HECRAS is a hydraulic model. Any hydraulic model will also give you the depth of flow, how it is varying with time, and also velocity. So depth and velocity, he tried to combine them and develop an index for say what you call as flood flood risk, and then based on that identified which are zones which are mostly he actually used these models to develop what happens in the climate change say, and then try to develop say flood risk models under climate change. So basically, say we can get the depth of flow. Most of these hydraulic models can give you depth of flow as well as velocity of flow. So these two are important parameters to decide about the risk of flooding. So depth, because it gives us how much, to what extent, for example, a building is getting inundated, to what extent it gets inundated. So based on that, you know how much area gets inundated and how much, what is the property loss. And velocity in sense, because velocity is important in sense because the velocity can affect the flow. For very high velocity can cause more damage than simple inundation with low velocity. So that's the reason why velocity is also important. So these two can be obtained by a hydraulic model. And if you depend purely on, like only, say, a hydrologic model like HHMS, that will not be able to give you this kind of parameters like depth of flow or this, say, velocity. That's the reason why we are trying to club a hydrologic model with a hydraulic model like HGRAS.
Okay, sir. Thank you, sir.
In fact, actually, urban areas more commonly used model is SWIM, so Stormwater Management Model, SWMM. But we didn't use, okay, we also use SWIM. I didn't show the results here. We also use SWIM, but the SWIM again has limitations because it is not, it's purely a one-dimensional model, and so we'll not be able to get the depth of flow and all these things. And in fact, okay, SWIM actually is improved, and then we have what we call as PC SWIM, which also gives the same thing like depth of flow and all those things. But PC SWIM is a commercial software.
Okay, sir. Yeah, thank you, sir.
Welcome.
Hello.
Hello.
So is it advisable to go for ACS curve number or physically based modeling framework for watershed runoff process?
No, if you if you want to go for a physically based model, curve number is not advisable. Curve number is more popular used because of its simplicity. Because finding curve number and then integrating that is easier. But actually, most of these hydrology models have the options. Instead of curve number, you can actually go for more versatile models like maybe like even synthetic meter model or maybe for say curve number is basically used for modeling the infiltration. So I think most of these models also have the option of going for green ant model or say hot touch model, all those things. I think it's always advisable to go for such models which are more physically based than simple SES curve number method.
Sir, and one more doubt, sir, in your case study. Actually, you are going for various changing land use, land cover changes with respect to constant rain, extreme rainfall, or with a different extreme rainfall condition with the land use, land cover changes you are going, sir?
In fact, our study actually discusses both of them. In fact, so because this is only a part of the study only I showed here, there's actually a study we have taken up under a project which is given by I think Ministry of Electronics and Information Technology. In fact, a collaborative project which you have taken up along with IISc Bangalore and BITS Hyderabad along with the NIT-Warangal. So we have taken this as a case study, whereas Bangalore they studied more on say IISc people they studied more on Bangalore. So the idea here is to use the technology, latest technology, to actually make use it for society. And so our say what we did for Hyderabad city is we, as one of the studies, first part we tried to actually study the extreme rainfall. And our extreme rainfall is being influenced by urbanization, like what I talked about at the beginning of the case study that I talked about. How the urbanization as well as the climate change are influencing the extreme rainfall, how the intensity of extreme rainfall is changing over the years. That's one part of study. And obviously that results in more flooding, frequent flooding. So how the flooding is taking place and how this climate change will influence in future the flooding and how the flood risk is going to change. And along with the change in the land use, this is like a combined study. That's what we did.
And so one more doubt, sir. You mentioned the word integrated modeling, sir.
Yeah.
Because hydrology works on basic equations, continuity equation, and hydraulic equations are different, sir. How do you integrate, sir? Integrate it, sir.
See, hydrology. See, basically, hydrology is also part of hydraulics. The only thing, the way we look at hydrology is different. As I said, it is like more of systems approach. But for example, if I take the flooding in a particular area, now your hydrology will only help us to identify what is the hydrograph or the flood discharge at particular location. Maybe if you go for a distributed model, I can get the, say for example, in the HHFS that we did, I can get the flood hydrographs at different locations along the catchment. Okay, at different points along the catchment. So that's what I can get, and then that I can use, make use in order, I can make use to route that flow through a hydraulic model. I'll use the hydraulic model now, where I'll try to study how this flood starts propagating, and then find out the say the depth or velocity or the inundation areas and all that things.
Okay, sir. Thank you, sir.
Any more questions?
Any more questions? Sir, there are, I think, one question is there in chat box, sir. Shall I read for you, sir?
Yeah, okay.
Yeah, someone has asked, which is the best method to find missing monthly stream flow data obtained from WRS?
Can you just read it again?
Yeah, which is the best method to find missing monthly stream flow data obtained from WRIS, sir?
See, we cannot say, in fact, there's nothing like a best method or this thing, because it's all basically when you have a missing data, you're filling. And whatever method you're using for filling data is basically a kind of statistical method. So no statistical method I can say is the best method or the right method. So we only have to actually try to study the different methods and find out which is more suitable in that area. So I cannot, it is case by case. We cannot really say this is the best method. So I think there's no such kind of right straight answer which you can say this is the best method to use. So you need to study, like you can actually always try to test the, say test, for example, you assume some known data is still missing and then try to study the various methods and then find out which method is working well for your case, and then use that further to actually fill the data. And that's what I normally advise if you want to really use these methods to fill the data.
Okay, sir. So any questions from participants, please? I think there are no questions from participants, sir. I think
okay.
We can stop here, sir. I think. Thank you very much, sir. Thank you.
Yeah, thank you. Thank you for this opportunity. And thank you all for your patient listening, and hope my lecture was useful for all of you. Thank you.
Thank you very much, sir. Okay, sir. Right, sir. So, participants, I think I have posted a attendance form. Please submit it. It is there in chat box, please. Another announcement, there is no session after this. I think he expressed his inability to take this session because he has some issues with internet and power connection. He said that he will take tomorrow. So I will let you know tomorrow morning when he will be taking that class. Okay. So as on today, there is no session after this, after now. Okay. So now we'll close this day. I mean. So you can submit your attendance, the Google form, which is posted in the chat box. And tomorrow is the last day. And if you see the schedule, there are 2 technical sessions, morning and afternoon. We have one session on stress management, which is a mandatory session as per the AICT. So after that, we have feedback from the participants, and then we'll conduct a quiz for you. Okay. The quiz, in quiz, there are 15 questions, and you have to, that will be again, that link will be posted in the chat box, and I think I will 20-25 minutes time duration for that quiz. So very simple questions. You can answer those questions within the time limit. I will tell you tomorrow. Okay. So that is a mandatory as per the AICT. You need to score 60% in the quiz and 80% in attendance. We will take the attendance from the I think log details from the Microsoft Teams. Okay. So that's all about. If you have any questions, please ask me now.
Hello.
Yes, sir. Please, sir.
How much will be the time limit
for quizzes, sir? Yeah. I think the questions, just I'm preparing the questions, sir. It is maybe 15 to 20 questions, maybe 20 to half an hour, sir. 20 minutes to half an hour. A very simple question.
That will be multiple choice question.
Yes, sir. Multiple choice questions.
So put it half an hour or so.
Yes, sir. Yes.
So time should be sufficient.
Yes, sir.
Time should be large. I mean, the time should be sufficient.
Yeah, sir. I will let you know full details tomorrow. Just I'm preparing that quiz question, sir. So based on the questions, I will give the time limit. If it is a 15 question, then I think 20 minutes is enough for you. If it is 20 questions, another 5-10 minutes I will give you. Okay, sir.
Yeah. For 15, at least it should be at least 25 minutes.
Okay, sir. No issue. No issue.
Okay.
Oh, no issue.
Thank you.
I will open that question while I think feedback is going on. Okay. No issue. Otherwise, at the end of the feedback, I will release that Google link and you can submit within 25 minutes. No issues, sir.
No, feedback is going on means we are attendance is going on.
No. Okay. I'm sorry. After the feedback only, I will release that quiz, sir.
Okay. So there will be another feedback process.
I think as per, sir, tomorrow session will be like this, sir. There should be a feedback from the participants also. Okay. So those who are interested to give their feedback, please let me know through the, I think we have a WhatsApp group. Either you can please mail me or you can, those who are willing to give you their feedback, please let me know through WhatsApp group or through mail or some other means. You can call to me also. I will read their names.
You can, there may be a suggestion.
Sir.
You can the feedback may be also through Google Form and so on. Everyone can.
That will take anyway, sir. That will take anyway.
So
okay.
that will be better.
If anybody want to speak 1 or 2 minutes, that
okay, like that.
That is also welcome. That is official I mean, formal feedback will take through the Google form. So, so during the valedictory session, if anybody want to speak 1 or 2 minutes, that is also welcome, sir. So that's right. Okay. So tomorrow is we have 2 sessions. Afternoon valedictory will be begin at 2:30. In that valedictory, quiz will be conducted for 25 minutes, and also anybody want to talk, that can also be permitted. I mean, and then we will finish it before 4 o'clock. Okay, sir.
Okay.
Right. Thank you very much. Thank you very much, sir.
Sir, Srinivasan, sir.
Yes, sir. Yes, sir.
Actually, I'm sorry to say, but then today, due to some internet issues, I could not attend both the sessions, well.
Okay,
so if you can post the videos a
Yes.
bit early today,
Okay.
I'll try to go through that,
Yeah.
because both the sessions are very, very important for me. But
Okay.
unfortunately, a lot of, from my side, there was some problem.
Yeah, I will do that, sir.
That
I will just
a bit early today. I will be grateful, sir.
So I will try to post as early as possible. Okay,
Okay.
all these 2 sessions. Okay. Right.
Yeah. Thank you so much, sir. Thank you so
Welcome.
Srinivasan, sir.
Yes, sir. Yes, sir.
It would be good if you kindly share the PPTs. You are sharing the YouTube.
Yes, sir. I'm asking all resource persons. So some are sending their PPT, some are not replying. Okay.
Sometimes it happens.
Yeah.
You have shared.
I am trying my best, sir, to take the PPT from all resource persons. Okay.
Yeah.
And,
because that will be also good for you also.
Yes,
that you
sir.
organize all this.
Yes, sir.
Because the ministry may ask any time or something like that.
Yes, sir. Yes, sir. Anyway, we have the recorded session, sir. That is one thing
That's okay.
Yeah.
Okay. That is the sessions are very important and very, very, very valuable for the researchers.
Yes, sir. Yes, sir.
So that's good. I congratulate you for the.
Thank you.
For organizing such, at a single place, we can get all the information related to the hydrology and this GIS remote sensing.
Yes, sir.
So that is very important, and the coupling of this modern technique with the for the estimation of hydrological parameters and all related to hydrological studies, that is very important. And in coming years, the hydrology or the water resources will be very important.
Right, sir.
Thank you very much, sir.
Thank you, sir. Thank you very much. But just students who are asking every time, there are very less employability in water resource, because when in government or private sector.
No. That's true.
Yeah.
But as far as employability is concerned, sometimes if you go for the general scenario, government employability is reducing, or there are less openings in government sector.
Yes, sir.
So once you are like today morning, whatever was the lecture related to the crop variability, crop insurance, and all these things, one of my student is earning a lot. In this, though he did PhD, and he is earning a lot in private sector.
Okay.
So and I see a big opening in the private sector, the multinationals or the national companies. Like the agriculture related laws has been implemented by the central government.
Okay.
Now, if contract farming or something is going on,
okay, sir.
So whosoever will be contracting to the farmers, will be knowing this information will be much more important, much important for them. Where ask for which type of crop and what should be, even though when the hydrological stress is there in the crop type, so they can say that when they have to irrigate the land, they will be continuously in contact with the farmers. So they can suggest to the farmer 2-3 days prior to the due date of irrigation that okay, you irrigate the land and otherwise your crop will be in stress, hydrological stress, something like that. So this technology, the students who are working in this area, they will be hired.
Yes,
of course, in government sector, because the in the university system, we are in the university or the research institute or in this NITs, IITs, the number of faculty positions are less.
Yes.
So that is, of course, I do agree with the students that in government sector there may be less opening, but in private sector they have, the only thing is that they have to learn the technique, this GIS and remote sensing techniques, and once they start implementing all these things in this any sector, any hydrological sector. Sector means any type of study, like crop, the flood, the other thing, drought or something like that, insurance, then that will benefit them.
Yeah, sir, because why I'm see, for example, in our state, Andhra Pradesh, there are more than, I think, 300 private engineering colleges are there, sir. In 300, more than 200 colleges are offering civil engineering in BTech graduation. Okay. But many colleges are offering structural engineering and geotechnical engineering. No single college is is offering this water resource engineering. So there are only 2 colleges in our state and our university, JNTU Kakinada and Andhra University. These 2 are offering water resource engineering. We also have started this program, I think 3 years back, with a lot of, since I joined in this university, I have been trying to introduce this program, but lot of with difficulty. I can succeed this starting this program. So that's the problem.
Srinivasan sir, if you want to do anything and any new thing, there will be problem, and you are the leader. Because you know, system the inertia. We are we are a student of physics. So system has inertia. Whatever is system has, that the system that should prevail. But if you want to do something new, you have to face the inertia. And that's why you are saying. But now you have become leader in this hydrological studies. So that is, and in Andhra University, there are several faculties in geophysics department.
Yeah, geophysics is there, right?
Yeah, they do hydrological, gravity, and all these things.
Yeah.
Okay, nice talking to you.
Yeah, thank you, sir. Thank you for your.
Thank you very much.
Thank you, everybody. Let us close today.
Thank you.
We'll, tomorrow it is UAV, sir. UAV remote sensing, unmanned aerial vehicle remote sensing. So Dr. PL and Raju, who is the director, Northeastern State Space Application Center, he will take that session, sir. Okay, at 10 o'clock. Okay.
Thank you.
Okay, sir. Thank you. Goodbye.
Bye.